This conference will now be recorded.
Hello everyone. Today we'll start with preparation methods of benzaldehyde, and we will also see the physical properties of aldehydes and ketones, and after finishing that there will be chemical properties of aldehyde and ketones. Preparation of benzaldehyde, the first method that we have here is oxidation of methyl benzene, and methyl benzene, it is also known as toluene, so you can also say it is oxidation of toluene. Here strong oxidizing agent such as potassium permanganate, if we use this reagent particularly, then it will give us benzoic acid. That means you have taken toluene, which is nothing but methyl benzene, you are treating it with KMnO4 and you are getting benzoic acid. But if it is some other oxidizing reagent which is not so strong like KMnO4, in that case we can get benzaldehyde, because we are trying to synthesize benzaldehyde. Our purpose is not to get benzoic acid. So if you have taken methyl benzene or toluene, you are treating it with KMnO4, which is very strong reagent, then you will end up with the product benzoic acid. But that is not the desired product. Desired product is benzaldehyde, and for that we have to use reagents such as chromyl chloride. So chromyl chloride, as you can see, this reaction, it is also known as heated reaction, and for this reaction we can also use another reagent combination that will also give same type of result, and that is CrO3 and acetic anhydride. So acetic anhydride is this molecule. In short, it is also written as AC2O. It is CH3, C double bond O, then O, C double bond O, CH3. And this is the actual oxidizing agent. So first what happens, this CH3, it is converted to CHOAC whole 2. That means benzene ring CH, one side there is one COCH3 group, that is OCOCH3, because AC is COCH3. So when I am saying OAC, it is OCOCH3. So first there will be formation of this type of intermediate, and finally it will be converted to benzaldehyde. But we will also see what is chromyl chloride. So chromyl chloride is this type of reagent. This is how it looks, and the reagent is CrO2Cl2. So now we are treating toluene with CrO2Cl2 in presence of carbon disulfide as solvent, and first there is formation of this type of complex, which is chromium complex. So if I am writing this complex, how it structure is actually, so O CrOH Cl2, that is coming twice. CrOH Cl, and on another side also same structure. So how it is written? It is written as CHOCrOH Cl2, which is coming OCrOH Cl2, which is coming twice. So that is why there is bracket and then 2. So this is the complex that will be formed first. So this is the complex between CrO2Cl2, which is chromyl chloride reagent, and toluene. Now if we are treating it with H2O+, means you are doing acidic condition hydrolysis, then this complex will be hydrolyzed to benzaldehyde, because benzaldehyde is the actual product that we are trying to synthesize. So two methods here we have seen. One is you can use the mixture of CrO3 in presence of acetic anhydride, and you can also use CrO2Cl2, which is chromyl chloride. So these reagents are not so strong like potassium permanganate, which is actually giving benzoic acid. But if you are using this type of oxidizing agent, which is specially made for getting benzaldehyde only, not acid, so we can use any of these two reagent combination if the starting material is methyl benzene. So this carbon CH3 methyl carbon, that is now converted to CHO group. The second method for preparation of benzaldehyde is side chain chlorination followed by hydrolysis. So side chain, when we are saying side chain, it is actually this methyl group. Again we have taken toluene. Side chain chlorination of toluene, it gives benzyl chloride first. So first we are getting pH CHCl2 is like this, chlorine, 2 chlorine, CHCl2. This is known as, you can call it benzyl chloride or you can also call it benzylidine chloride. Okay. And further, when you are hydrolyzing it, then it will be converted to CHO. So this is another method. It is called side chain chlorination, because first there is chlorination, then you are doing hydrolysis, you are getting benzaldehyde. Number 3, Gatterman-Koch reaction. So in this reaction, starting material is benzene, and the reagent combination we are using carbon monoxide HCl. There is also presence of Lewis acid AlCl3 and CuCl. Here we are getting benzaldehyde. So this reaction, you can say it is another variant of Friedel-Crafts acylation. So in Friedel-Crafts acylation, normally what we use reagent combination. One is acid chloride RCOCl and Lewis acid, and Lewis acid is mostly AlCl3. So what happens in Friedel-Crafts acylation? Starting from benzene, RCO group is introduced by replacing any of the hydrogen of benzene. So here also you can find some similarity, but in our case it is not RCO, it is HCO group which is inserted. So it is a kind of variant of Friedel-Crafts acylation. In this method, reaction of carbon monoxide and HCl, it generates first an intermediate. Okay, so let's see, that is the second point, whatever is mentioned, reaction of carbon monoxide and HCl. First, CO reacts with HCl, there is formation of some compound which is reacting with benzene and making an intermediate. So this is the mechanism. If we look deep into the mechanism, this is carbon monoxide molecule in presence of HCl, there is formation of this type of HC triple bond O plus. Now AlCl3 is the Lewis acid. It will interact with this oxygen and carbon is now positively charged. Here benzene ring is acting as nucleophile and this part is acting as electrophile because it is electron deficient. So that is why the pi bond, that is the pi electron density of benzene ring, it is now attacking the carbonyl carbon, which is basically positively charged now. So as a result, what will happen? As this pi bond is broken, there will be CC, suppose this carbon and this carbon, these two carbon, there will be bond formation, and as a result there will be positive charge generation at this position. Now you can consider any of these resonance structure. Suppose this is the first structure, positive charge is generated. Further resonance is possible. You can also draw the resonance structure. So see, positive charge is here. Now after shifting of this double bond, positive charge, it is shifted here. Then again this double bond, when it is changing its position, now the positive charge is here. So these are the different resonance structure possible. And the average structure is this one, where it is written in this way, dotted line. So it means it is average of these three structure. So finally what will happen, as you can see in this three structure, aromaticity is lost. So what will happen, this H, it will be removed in the form of H plus. So CH bond will be broken and there will be double bond formation in this position and aromaticity will be regenerated. Fine. So in this method, reaction of carbon monoxide HCl generate an intermediate. So you can say this is the intermediate which reacts like formyl chloride. So formyl chloride is basically HCOCl. So if you remove this Cl, the remaining part HCO, you can find some similarity here. So that is it is written. It reacts like formyl chloride, which is HCOCl. So by Gatterman-Koch reaction, starting from benzene, you can prepare benzaldehyde. You have to use CO and HCl, AlCl3, CuCl. After finishing preparation methods of benzaldehyde, total 3 methods we have seen. Now we are starting preparation of ketones. First method is from acid chloride or acyl chloride. Now when I'm saying acid chloride, it is basically derivative of carboxylic acid. Carboxylic acid is RCOOH, and acid chloride is RCOCl. This is acid chloride. It can also be called as acyl chloride. Here we have taken this acyl chloride, and see, the ketones are easily prepared by reaction with suitable dialkyl cadmium with acid chloride. So first there will be we have to prepare dialkyl cadmium. This dialkyl cadmium will react with acid chloride. So this is the second step where dialkyl cadmium R2CT is reacting with acid chloride. 2 molecules of acid chloride we have taken, 1 mole R2CD. But before that, in the first step, if you see how this R2CD is formed, that is mentioned. This for preparation of this R2CD, which is dialkyl cadmium, 2 alkyl groups attached to cadmium, we are taking the help of Grignard reagent, 2R-MgX. This is the general structure of Grignard reagent. In presence of cadmium chloride dry ether, R2CD is formed. So 2 molecules we have taken. So these 2 R groups attached to CD and MgXCl that will be formed byproduct. Now this R2CD dialkyl cadmium is reacting with R prime COCl because we have already used the group R. It is mentioned here as R prime. What will happen? This R group will come from CD and it will take the place of Cl, and Cl will be removed. So you are getting back CdCl2. But what we are getting finally? We are getting ketone. Okay. Now the question may arise, why we are not using Grignard reagent in this reaction directly? Because we can easily use Grignard reagent RMGX plus R prime COCl. So what will happen? This R group will attack here, which is basically it has carbanionic type of nature. You can say it can act as nucleophilic. So this Cl will be removed. But the problem is Grignard reagent is very, very reactive. That is, compared to dialkyl cadmium, obviously it is more reactive. So you cannot stop the reaction at this position. Further, there will be attack by this R minus, which is coming from Grignard. It will attack here and there will be formation of alcohol. But our purpose is not to produce alcohol. Purpose is to produce ketone. So that is why you cannot use Grignard reagent. It is more reactive than dialkyl cadmium and it converts the ketone into tertiary alcohol, 3-degree alcohol. So that is why we cannot use this reagent. Now this is a general example. If you take actual example, suppose R2CD where R group is ethyl group, that is Et2CD, and acid chloride we have taken acetyl chloride, CH3COCl, which is a derivative of acetic acid, CH3COOH. In presence of dry ether, we are getting CH3CO, CH2CH2. So this is the R group which is coming from acid chloride, and this is methyl, and the other side of carbonyl, which is ethyl, that is coming from the cadmium reagent. Okay, so in this way we can prepare ketones. Second method. Now the starting material is nitrile. Ketones can also be prepared by the reaction of Grignard reagent with suitable alkyl nitrile. Okay, so when we are saying nitrile, general structure you can write RC triple bond N, but here we have taken acetonitrile, CH3 C triple bond N, and the Grignard reagent we have taken ethyl magnesium bromide. Dry ether, always whenever we use Grignard reagent, it is ether solvent and it must be dry. Here this is the alkyl group which is coming from Grignard reagent. It will have some carbanionic nature. So this will attack at this carbon. Triple bond between carbon and nitrogen will be broken. There will be negative charge over nitrogen. And this is the positive part of Grignard reagent because CH3CH2 is the negative part. There is polarity minus and plus. So the positive part that will be now attached to the negatively charged nitrogen. So it is charge is balanced. This is the addition product, but this is not obviously the final product. It is written within third bracket. That means it is not final product. It will be generated, but finally, when you are doing hydrolysis in presence of acidic condition, this NMgBr, that is replaced by oxygen, right? Nitrogen is removed in the form of ammonia, and this is the other byproduct, MgOHBr. But what we are getting? We are getting butanone. So butanone, it is actually ethyl methyl ketone. This side we have ethyl, other side we have methyl. Ethyl is coming from Grignard reagent, methyl is coming from acetonitrile. So suppose if you want to make, that is, if you know what type of ketone structure you actually want to make, you have to choose the starting material accordingly. Okay, so if the structure is like, if I am saying in general RCO R prime, so this one R group must be present in Grignard reagent or the nitrile, and the other R group that should be present in Grignard or nitrile. Okay, now instead of taking CH3CN, suppose if you have taken hydrocyanic acid. Now hydrocyanic acid is HCN. Here you have taken RCN. R is methyl nitrate. But suppose you have taken hydrocyanic acid, HCN, then what will happen? Now obviously you will get aldehyde because this part is here. But if this is H, obviously this group is H. And if it is H, it is aldehyde, it is not ketone. So if your purpose is to make ketone, you cannot take hydrocyanic acid, because in that case you will be getting aldehyde, right? So same reaction, only difference is here you have H. So see, ethyl group which is coming from Grignard reagent. In the second example, methyl group which is coming from Grignard, this H, it is already present in AC, right? And after acidic hydrolysis you are getting aldehyde, not ketone. Method number 3. Now the starting material is benzene, but you can take any derivative of benzene, that is substituted benzene. And this reaction is very common reaction, which is Friedel-Crafts acylation, not alkylation. Alkylation, if I say, then it will be R group, alkyl group that will be attached to benzene. But here we are trying to prepare ketone, right? So that is why Friedel-Crafts acylation you have to do. And remember this method, this third method that we are discussing in this particular slide, that is for aromatic ketone. Ketone structure is RCO R prime. Now one of this R group, if it is aromatic in nature, suppose this is not R, this is Ar, that means it is aryl ketone, or you can say aryl alkyl ketone, because one side you have aryl group, another side you have alkyl group, or it may be both side you have aryl group, that is also possible. So if you want to make this type of ketone, you have to do Friedel-Crafts acylation. Now this reaction is possible only with benzene, or it must be activated benzene, because when I'm saying activated benzene derivative, that means this pi electron density in benzene, that must be very rich. It must be very electron rich, because here RCOCl, that is the source of electrophile. Here the actual electrophile is RC plus double bond O. After removal of this carbon chlorine bond, this is the actual electrophile. So this is example of electrophilic aromatic substitution. Here electrophile is generated from RCOCl or ArCOCl, and benzene ring is acting as nucleophile. So reaction between nucleophile and E plus. This is electron deficient, this is electron rich. So if there is some group present, I am writing in general, suppose G is any group which is present in benzene, which is having some donating character, then it will be helpful for the reaction. Now instead of acyl chloride, you can also use anhydride, because in case of anhydride also, which is having structure like this, RCOO, COR. So here also same electrophile can be generated, RCO plus, right? So you can use either RCOCl or ArCOCl. Ar will be, if you are using ArCOCl, then both side there is Ar, so it will be diaryl ketone, this one. And if it is RCOCl, one side benzene, another side alkyl, then it is alkyl aryl ketone. Okay, so instead of taking RCOCl, you can also take anhydride. So the second example, here we have taken methyl benzene. Now methyl, it will have some donating effect, and this is acetic anhydride. In short, you can write Ac2O. Lewis acid must be present, anhydrous AlCl3, and in this case, see, with respect to methyl, the electrophile, which is CH3 C double bond O plus. This is the electrophile. Now this electrophile can be inserted at 4 position, para position with respect to methyl group, or this may be inserted at 2 position with respect to methyl group. Both are possible, right? And the other part of the reagent Ac2O, that will be removed in the form of CH3COOH. So you can get para product, ortho product, that is you can get mixture of these two, and this is the byproduct. Fine. Now after finishing the preparation methods for ketones, physical properties of aldehyde and ketones, that is in general we will see the physical properties of both these compounds. Formaldehyde is a gas at room temperature. So first we will see physical state, that is whether it is gaseous, liquid or solid. Formaldehyde, which is the simplest aldehyde, ACOH, this is gas at room temperature, and acetaldehyde, CH3CH, it is a volatile liquid. Now formaldehyde, ACHO, that is the first member. Now this H, if you replace with methyl, it will be the second member, acetaldehyde. Now after this, starting from number 3, 4, 5, all the other aldehydes and ketones up to C11, that is total number of carbon 11 up to, they will be colorless liquid. So see how the physical state is changing as you are increasing the number of carbon. When it is the simplest structure, it is gaseous. When you are moving to the next possibility, which is CH3CHO, now it is volatile liquid. That means it is liquid, but there is some volatile nature. It can be easily converted to vapor state. But as you move further up to C11, now it is colorless liquid. But if you move after that, C11, C12, C13, 14, all are solid. Because now number of carbon atoms are increased, number of hydrogens are also increased. Molar mass when increasing, the physical state will be changing towards solid. Next is odor. When we are talking about lower aldehydes, there is sharp, pungent odor. But when the size of the molecule is increasing, then the odor becomes less pungent and more fragrant. That means now that it is having some soothing smell. Polar nature. Aldehyde and ketones, they are polar in nature because there is presence of C double bond O. And C double bond O, these two elements, oxygen is more electronegative than carbon, and as a result, if you keep the sigma bond and break the pi bond, positive charge will always be over carbon, negative charge will always be over oxygen. So here we do not have any charge, but when you have keep the bond, there will be fully developed positive charge and negative charge. And if you are breaking the bond partially, like this dotted line I am using, then partially negative charge, partially positive charge. Fine. So because of this difference in electronegativities, there will be some polarity, and this also implies that dipole-dipole interactions will be present between molecules of aldehydes and ketones. So one that is, here you can see positive charge is generated. There are obviously two more bonds. So this positive charge and this negative charge over oxygen, that is, suppose two molecules are there, positive charge over carbon for one molecule interacting with the negative charge of the oxygen of the other molecule. So in this way, dipole-dipole interaction is possible in aldehydes and ketones. Hydrogen bond. Aldehyde and ketones do not form any hydrogen bond between themselves. Now it means that suppose you have two molecules of RCOH. Now if you look carefully, here oxygen is the electronegative atom. But directly with oxygen, you do not have any hydrogen. Hydrogen is attached to carbon, right? And if you consider RCOR, that is structure of ketone, suppose R prime, then also there is no hydrogen directly attached to oxygen. So that is why within this molecule, hydrogen bond formation not possible. Here, this hydrogen even cannot make hydrogen bond with the oxygen of the other, because the condition for hydrogen bonding is that hydrogen must be attached to some electronegative atom. It should be either oxygen or nitrogen, and best if it is fluorine, right? So that is why, as in these molecules, there is no hydrogen directly attached to oxygen. So hydrogen bond formation between two aldehyde molecules or two ketone molecules, that is not possible. But hydrogen bond is possible with other molecules such as water, alcohol, carboxylic acid. Now why it is possible? Because in water, the hydrogens attached to oxygen. In alcohol, hydrogen attached directly to oxygen. Carboxylic acid, hydrogen attached to oxygen. That means all these hydrogens are active. Now this hydrogen can interact with the oxygen of carbonyl, carbonyl group. So that is why hydrogen bond formation possible with all these molecules. But between two molecules of aldehyde or two molecules of ketone, hydrogen bond formation is not possible. Okay. Number fifth point for physical properties of aldehydes and ketones, solubility. Now here we are talking about, we'll talk about solubility in water first, then we'll see organic solvent. So when it is lower members, look at this table. Formaldehyde, that is the simplest structure of aldehyde, then acetaldehyde, then acetone, the first ketone, simplest ketone possible. All these three molecules, they are very much soluble in water. Their solubility is very, very high, for 400 gram per liter of water. So it is a high value, very much soluble. Then further you are increasing the carbon, butanone, that means CH3, CO, two more carbon, total 4. Now also it is soluble. Then propanol. Propanol is 3 carbon. Sorry, CH3, CH2, CH. Soluble. Butaldehyde. This is also aldehyde. That means 4 carbon, 1, 2, 3, 4. Then aldehyde. This is also soluble. Now we have salicylaldehyde. Now, salicylaldehyde is benzene ring. There is OH. So now molecular weight is increased. And as molecular weight is increasing and the carbon hydrogen part, that is the non-polar part, is increasing, then also there is a possibility that solubility will decrease. So now it is insoluble. See? Then benzaldehyde, that is benzene ring, CHO, insoluble. Acetophenone, pH COCH3. So this is insoluble. The lower members of aldehyde ketones such as methanol, propanone, etc., they are miscible with water in all proportion because they can form hydrogen bond with water. So see, hydrogen bond formation with water. Here two molecules that you are seeing having R and R prime both side of the C double bond O, but any of these group you can consider as if it is hydrogen, and in that case it will be aldehyde. Now as the length of alkyl chain increases, the solubility of aldehyde and ketones, it will decrease rapidly because number of carbon atoms increases in chain. So when number of carbon atoms increases, though these three are aromatic, so we cannot say it is chain, but you can also see that the first three, they are very much soluble, and suddenly when you are going from 3 carbon to 4 carbon, now it is becoming comparatively less soluble. Fine. Then here, in case of aromatic molecules also, here number of carbon atoms are increasing. So when number of carbon atoms are increasing and also the hydrogen atoms, then what happens? The non-polar part is basically increasing because oxygen number is fixed. There is only one carbonyl group. But keeping the oxygen number fixed, you are increasing carbon and hydrogen. So non-polar part, hydrophobic part is increasing, so obviously solubility in water will decrease. But if you consider non-polar solvent like organic solvent, not always non-polar, I mean to say non-aqueous solvent, that is organic solvent like benzene, ether, methanol, chloroform, then they are fairly soluble. Because always polar compounds, they prefer polar solvent, that is their solubility is good in polar. But if the molecule is non-polar, that is when you are moving from polar compound towards non-polar, because when you are increasing the number of carbon, chain length is increasing, non-polar part is increasing, so gradually they will prefer no, that is less polar solvent. And you can also see methanol is more polar compared to benzene, though both are organic, both are non-aqueous, but still there may be some difference. So I'm trying to say more is the non-polar character introduced, it will always prefer more non-polar solvent. So that is why in water you are having solubility problem, but if you take organic solvents, so all these solvents are less polar compared to water, so that is why now solubility is possible. Number 6 point, boiling point. It is because of weak molecular association in aldehydes and ketones arising out of dipole-dipole interaction. So when interaction between molecules are very low, that means what? You don't have to break that is, you don't have to provide very high energy to break the molecules. So here you can see, suppose we have aldehyde or ketone molecules. So negative charge of one oxygen interacting with the positive charge of another carbon, then it is going on the chain system, but it is not the hydrogen bond. This is dipole-dipole interaction. And if you compare the bond strength of these different types of intermolecular interaction, hydrogen bond is one type of intermolecular interaction, dipole-dipole interaction is another type, van der Waals interaction is another type. Now hydrogen bond compared to dipole-dipole, it is having more strength, and dipole-dipole is having more strength compared to van der Waals. Van der Waals forces are mostly seen in non-polar compounds, where polarity cannot be generated. So you will see in pentane, that is alkane molecules, van der Waals force is the most important intermolecular interaction that is possible. But when it is aldehyde or ketones that we are discussing right now, then dipole-dipole interaction is present. So here this dipole-dipole interaction you can see. Fine. Now when you are trying to, that is boiling point means what? You are converting from liquid state to vapor state, right? That means you have to increase the gap between the molecules. Now for that purpose you have to break this bond, but if the interaction is very weak, you don't have to provide much energy. So that is why boiling point will be low compared to that case where hydrogen bond is present, because to break hydrogen bond you have to provide more energy compared to dipole-dipole attraction. So that is why if you look at these compounds, here we have taken different types of compounds. But one important point that you have to keep in mind, their molar mass should be very close to each other, because molar mass is another factor depending on which boiling point may vary. It may increase or decrease. So when molar mass increases, basically boiling point also increases. So that is why keeping this factor constant, here all the values that you are seeing, it is 72 to 74, so they are more or less same. So we are keeping this factor constant so that we can compare the other factor on which boiling point is dependent, and this other factor is intermolecular bond strength. So we have taken ether, we have taken alkane, then aldehyde, ketone, alcohol, carboxylic acid, all are having same molar mass. But if you look at the values, the first two, that is ether and alkane, they are having lowest boiling point, because in this case there is no dipole-dipole interaction, no hydrogen bond, only van der Waals interaction is prevalent. So that is why, as it is very weak, so to break this force you don't have to provide much energy, boiling point is very low. Then for aldehyde and ketone, now the value is almost double, right? 76, 80. That means now you have to break dipole-dipole attraction, not van der Waals. So that is why you have to provide more. But if you have alcohol or carboxylic acid, now you have to break hydrogen bond. So here it is hydrogen bond. For the middle two, it is dipole-dipole interaction. And for the first two, it is van der Waals. So that is why gradually the boiling point is increased. These two are having very, very high value. Fine. Aldehydes and ketones have relatively high BP compared to hydrocarbon and ethers. That is the first two, diethyl ether, pentane. Obviously comparable molecular mass. Otherwise, if it is not same, we cannot compare. The boiling points of aldehydes and ketones much lower than alcohols and carboxylic acid, because in this case, you have to break hydrogen bond, which is more energy requiring process. Okay. So in this way, you can compare the boiling points of ether, alkane, aldehyde, ketone, alcohol, carboxylic acid. Okay. So after finishing physical properties, next is chemical properties of aldehyde ketones, and this is actually involves so many different types of reactions. This is really very huge amount of reactions that you are going to see, and we have here this flowchart which will help you to understand, though it is not that all the reactions that you are seeing here, it is not that the chemical properties of aldehyde ketones are limited to only these reactions. There are so many other reactions also, but if we that is according to syllabus, this much is enough. So first we have nucleophilic addition type of reaction, and under this type we have all these ACN addition, NaCO3 addition. So when I am saying nucleophilic addition, that means some nucleophile will attack the carbonyl carbon, because this carbon is electron deficient. So some nucleophile which will be generated from all these reagents basically. Okay, so that is why it is nucleophilic addition. And after that, oxidation, the different types of oxidation, three categories we have: oxidation of aldehyde, oxidation of ketone, and haloform reaction. Then reduction. Now reduction of aldehyde and ketone, it may be to alcohol, it may be reduction to hydrocarbon, reduction to phenol. Then reaction involving alpha hydrogen. Now what is alpha hydrogen? Now this is carbonyl carbon. With respect to this carbon, these two positions are alpha. So if in these two positions there is carbon or hydrogen, suppose this is hydrogen or carbon, aldehyde hydrogen, ketone carbon. So with this, that is in this alpha carbon, if there are some hydrogen present, as they are attached to alpha carbon, so that is why these hydrogens are alpha hydrogen. So sometimes what happens, reaction can also happen with this alpha hydrogen. So these two reactions, they are involving this alpha hydrogen. So that is why there is separate category. And then there is some other reaction, or we say miscellaneous reaction, different types, which you cannot categorize in such a way. So you can also write it as if it is other reaction, though only here 6 reactions are mentioned. But if that is we get time, we will also discuss some other reactions. That is not just these 6, some 2 to 3 more reactions also we can discuss. So first we will cover nucleophilic addition, and under this we have addition of hydrocyanic acid HCl, then sodium bisulfite, addition of alcohol, addition of Grignard reagent, and addition of ammonia, and not only ammonia and its derivatives also. Okay, so how you get derivative? If you replace one of these H with some other group, there is derivative. For example, NH3, if you replace one H with OH, then it will be NH2OH. So this is, you can say it is derivative of ammonia. Fine. So before going to nucleophilic addition, first we have to understand that what is the mechanism of nucleophilic addition, because if you know this properly, you will be getting proper idea about all the examples that we are going to discuss. So this is a common mechanism for any nucleophilic addition. There may be a little bit difference in each reaction, but some common points will always be there. Here, remember we have already discussed the structure of carbonyl. So now this carbon and oxygen, this carbon, there will be polarity because carbon is less electronegative, so positive charge will be over carbon, negative charge over oxygen, and nucleophile will be generated from the reagent that we will use. Directly we cannot use nucleophile. So suppose if you take the example of HCN, here you are using HCN, but actual nucleophile is Cn minus. So directly we cannot use nucleophile, we will use some source as a nucleophile. So this nucleophile is added, the pi bond between oxygen and carbon will be broken, there will be negative charge over oxygen. So see, this is the negative charge. Now the next step is very fast. Here E plus is mentioned. Don't be confused. Here by E plus we are basically trying to say the other part of the reagent. Now in this particular case, if you consider HCl, the other part of the reagent is H. So in this case, E plus will be nothing but H plus, and the OE that you are seeing here, that will be OH. So it may vary depending on what type of reagent you are using. So this type of reactions, that is the nucleophilic addition, is the most common reaction for aldehydes and ketones. That is why we are discussing it at first. Here, carbonyl carbon, as it is less electronegative compared to oxygen, there will be some small degree of positive charge. Nucleophile will attack the carbonyl carbon. It will form a new carbon nucleophile sigma bond. So this is the new nucleophile, carbon nucleophile sigma bond. At the same time, 2 electrons from C double bond O, it will move to the most electronegative oxygen. So as you can see, negative charge is present here. Now this results in the formation of tetrahedral intermediate. So this is actually the tetrahedral intermediate within third bracket, right? You can also call it alkoxide ion because alkoxide ion means this type of ion, oxygen carrying negative charge, rest of the part it is attached to some carbon fragment, right? So this is alkoxide. In general, you can write alkoxide as if it is RO minus type. So alkoxide is generated, it is tetrahedral intermediate, and interesting thing is, at first, before the nucleophilic attack, this carbon is sp2 hybridized. Hybridization we have already discussed. Remember in structure, one slide we have discussed where structure of carbonyl group in detail we have seen. So it is sp2 hybridized, but after nucleophile addition, now the hybridization is sp3. And for sp3, we know it is tetrahedral, right? Now the same mechanism that you are seeing here, you can also consider it in this way. Here C double bond O, it is taken in this square as if it is, we know it is planar because it is sp2 hybridized, so it is planar. So to have this idea of planarity, we have this square here. Two other groups are attached, suppose A and B, to carbonyl. Now the first step where nucleophile is attacking and the pi bond between carbon and oxygen broken, that step is slow step. And you can see here the tetrahedral intermediate. Initially it was planar, but now hybridization is changed. It is sp3, and for sp3 we know the angle is 109 degree 28 minutes, right? So now it is no longer planar, which is clear from the picture also. In the next stage, H plus, which is analog of this E plus here, you can also write E plus, that will be attached to this O minus. Okay, so it will be OH or OE. So this is the final addition product where the carbon is actually sp3 hybridized. Fine. So this is the common mechanism that will be applicable for all the reactions that we are going to discuss. Now, before going to examples of nucleophilic addition, one thing that you have to understand is relative strength of aldehyde and ketones. So, relative strength of carbonyl carbon. Now, this strength you can consider from two points of view. The first is inductive effect. So if you consider inductive effect of the R groups that is present in aldehyde or ketone. So in aldehyde you have only one R group, in ketone you have two R group. So when there is two R group, inductive effect will be very high for ketone. So more electrophilic is the carbonyl carbon, more readily nucleophilic addition will take place. So for aldehyde, here only one alkyl group is playing the plus I inductive effect. That means the carbon of aldehyde and the carbon of ketone, if you compare, which one is more electron deficient? Obviously, the carbon which is present in aldehyde, because the carbon in ketone, from both sides there is some plus I effect, but here only from one side there is plus I effect, and plus I effect means it is increasing the electron density. So when it is increasing electron density, the tendency for nucleophilic attack, that tendency will be less and less. So if you compare the nucleophilic attack in case of aldehyde and ketone, in which case it will be better? Obviously it is for aldehyde, because here inductive effect is less. So more electrophilic is the carbonyl carbon. Electrophilic means more electron deficient. More readily the attack by the nucleophile is possible. So if you compare the reactivity of aldehyde and ketone, obviously aldehyde will be more reactive. There is another point of view based on which you can understand that why aldehydes are more reactive, and that is because of steric effect. So in case of ketone you have two R group, in case of aldehyde you have one R group, other side you have very small hydrogen. So suppose one side is fixed, both side you have methyl, but the other side you have H and R prime. Now H is very small, so when nucleophile is attacking, remember in the last slide what you have seen, before nucleophilic attack it is planar, and surrounding carbon there is total 3 atoms present, but after attack now it is tetrahedral, total 4 atoms are present. So obviously steric hindrances increase surrounding carbon, so it will that is a nucleophile, when it will approach towards the carbon, if there are some small group present, the attack by the nucleophile it will be favorable. So in case of aldehyde, suppose one of this group is small H atom, hydrogen atom, so the attack by the nucleophile will be preferred here. So this is steric point of view. So we can describe the relative strength of aldehyde and ketone. Actually aldehyde is more reactive, that is on the basis of inductive effect and steric effect. So now we can draw the conclusion. In general, aldehydes are more reactive than ketones towards nucleophilic addition, that is towards nucleophilic attack, because of inductive effect, and the other reason is steric effect. So from both point of view, aldehyde is winning over ketones. Now here we have some molecules where you can see the reactivity order. Suppose the nucleophile is fixed. Suppose the nucleophile is Cn minus. Just arbitrarily I am saying. See if it is nucleophile. Keeping the nucleophile same. If you are changing the substrate, that is a substrate containing carbonyl carbon, you are comparing different carbonyl compounds. So you cannot change nucleophile. You have to keep the other factor constant. So keeping the nucleophile fixed, if you have different types of carbonyl compounds, see here most reactive is formaldehyde, because this is the simplest structure possible. Both sides you do not have any R group, you have simple H, no question of inductive effect, and steric point of view, this is very small molecule. Nucleophile can easily attack. So that is, it is most reactive. After that, CH3CH, acetaldehyde. Then 3-carbonaldehyde, propanol. After that, we have ketone. So see, this is also 3 carbon, this is also 3 carbon. But this is aldehyde, this is ketone. So aldehyde is more reactive. Then now we do not have any aldehyde. All these 4 examples, all are ketone. Now if you compare ketone, here you have 2 methyl group both sides. In the next structure, 1 methyl group is still there, but left hand side 2 carbon. So it is 2, 1, this is 1, 1. Then 2, 2, and here see, this is so large, that is group Me3C, carbon having 3 methyl, no hydrogens. So that is why this is the most unreactive among all these molecules. So in this way you can compare the reactivity order of all these molecules based on 2 points. One is inductive effect, another one is steric effect. So now there will be different examples of nucleophilic addition. The first reaction that we are going to see is addition of HCl. Here the actual nucleophile is Cn minus. Attack of Cn minus on carbonyl carbon followed by protonation. It gives cyanohydrin. So this type of molecule is known as cyanohydrin. Cyanohydrin, you can also convert it to hydroxy acid when it is treated with H2O under acidic condition. So this is, you can say, application of this type of cyanohydrin molecules. So what will happen now? This CN will be converted to CO2H, H3C, CO2H, HOH. That means this is hydroxy acid. You have acid group, you have OH group. So that is why it is written here, cyanohydrin can be converted into hydroxy acid by acid hydrolysis. You can also do reduction reaction of cyanohydrin. It will give you hydroxy ketone. So if you are doing reduction, now CN will be converted to NH2. Rest of the part, there is no change. So now it is hydroxyamine, because you have hydroxy, you have amine. So this type of compound is very, that is, you can apply it for different purpose. Once it is formed, from this you can make hydroxy acid, you can make hydroxyamine, fine. Now this you can prepare starting from aldehyde, mostly aldehyde examples you will see, because they are more reactive compared to ketone. But with ketone also it is possible. Nucleophile is attacking, we are getting this tetrahedral intermediate, and finally this H plus that will be attached here, which is protonation, and we are getting cyanohydrin. Next reaction is addition of NaHSO3. NaHSO3, if I write the molecule, one is Na plus, that is the positive part, another part is O, that is SO3H. Now SO3H, if we consider, there is negative charge present over oxygen. Now this negative charge which is present over oxygen, that can attack this carbonyl carbon. So HSO3, that is actually the nucleophile. Sodium is basically the counter ion. So once it is, that is when it is attacking, the bond between carbon and oxygen, pi bond will be broken. So this is the tetrahedral intermediate that will be generated. And finally, there will be proton transfer. So this H, now it can come here, and there will be negative charge over oxygen, and that negative charge can be balanced by sodium, because sodium ion is already present. So the final molecule that we are getting is like this, OSO3Na. Okay. It is due to weak molecular association in aldehydes and ketone. Sorry, these points. Okay. Actually, this slide, let me erase it. This is the actual slide that I want to keep. So the first reaction that is already discussed. Second reaction, you can see the mechanism better in this case. So HSO3 minus, you can write it first as H plus and SO3 2 minus. Now this SO3 2 minus, the structure is like this. Okay, so the negative charge that is present over oxygen, now it is making sulfur oxygen bond, and the attack is occurring through sulfur. Okay, so pi bond between carbon and oxygen is broken. We are getting this type of structure. So this structure you can also write it as fine. So this is SO3 minus. Now this is bisulfite addition product. But in the medium we also have HSO3 minus. From this HSO3 minus, this oxygen O minus, it will take this proton, and as a result now it will be converted to OH. And the other part, here we have negative charge, you can also write the counter ion like this. Now the SO3 2 minus that is generated as byproduct, that can attack the next ketone molecule or aldehyde molecule, because this is the actual nucleophile. Basically even HSO3 minus is also not actual nucleophile. Further ionization you can do. This is the actual nucleophile. Now this reaction, you can see there is some equilibrium sign. It has one specific application. So what is the application? This reaction finds application in the separation and purification of carbonyl compound. So suppose you have any carbonyl compound, aldehyde or ketone, it is mixed with some impurity. So this is aldehyde or carbon. In general, I am writing as it is CO with some impurity I. Now, if this mixture you are treating it with NaHSO3, only the C double bond O, that is the carbonyl compound, will react with NaHSO3, not the impurity. So as a result, what will happen? After the reaction, this bisulfate at sulfite, not sulfate, this bisulfite addition product, that is water soluble. That means this product, final product, is water soluble. So when it is mixed with impurity, you can add water, and as a result what will happen, as it is water soluble, impurity is not water soluble, so you can separate it by filtration, and then the solution filtrate that you are getting, which is containing the addition product, if you are treating it with mineral acid, then it will generate the carbonyl compound back. So one question regarding this we can explain. Sodium bisulfite is used, that is NaHSO3 is used for purification purpose. So how you can explain it? So suppose you have this acetaldehyde plus impurity. So impurity is not reacting with NaHSO3, only this one is reacting. This is the addition product plus impurity, but when you are treating it with water, only this one will be soluble, this will remain as solid. Now the soluble part, filtrate part, if you are treating it with mineral acid, then you will get back the original starting material. So aldehydes and ketones form addition compounds with NaHSO3, but impurities will not make addition compound. Further, when you are doing hydrolysis, you can, that is mineral, that is H plus must be present, we get pure aldehyde or ketone. So in this way, this reaction, because of its reversibility nature, we can use it for this special purpose to remove impurity, that is for the purification purpose of aldehyde and ketones. So we will end here. In the next class, we will see some more examples of nucleophilic addition reaction, and after finishing that, there will be some other reactions of aldehydes and ketones. Thank you for listening.